Welcome, everyone. We have here the worksheet for Chapter 19, which is Chapter 19 is on nucleophilic addition reactions to aldehydes and ketones, and also goes over some methods for preparing aldehydes and ketones. And we have some questions where you're given essentially the starting material and the reagents, and you need to fill in the structure of the product. And then we have some mechanisms as well. So these are just some typical Chapter 19 questions. Doesn't cover every single reaction in the chapter, of which there are many. And admittedly, the mechanisms are rather steppy. Let's say there's a lot of steps in these mechanisms, but I'm hoping to make it clear in class. As I speak, we've only done just one lecture on Chapter 19, but I'm hoping that as a result of class, we can make it clear that really all these reactions are the same thing again and again. And not only that, they consist of patterns that we will find repeatedly in other reactions in other chapters. So Chapter 19 is a really critical one in this semester, I would say, and especially considering that, as I believe I've mentioned in class, carbonyl chemistry figures predominantly in any organic chemistry 2 class, pretty much regardless of the professor and the textbook and the institution at which it's being taught. So the first question, or the first set of 3 questions really, asks to draw exactly one neutral organic compound corresponding to the major organic product. We also need to account for any applicable relative stereochemistry. I think in these 3 cases there isn't going to be, but we'll go over that when we get there. And then again, a reminder, with this type of question, the equations are not necessarily balanced. You've probably noticed by now that we organic chemists are not terribly picky about balancing equations, certainly not as much as you were brought up to do regularly in Gen Chem. So we can be kind of sloppy about that. We often ignore inorganic side products, for example. So let's look at this first one, which, by the way, has a chiral carbon in it. I don't know if I ever noticed that before I gave this question on the exam a couple of semesters ago. But since it doesn't specify the stereochemistry there, we'll just do the very same thing in the product. We won't specify the stereochemistry. So diisobutyl aluminum hydride is a reagent that we've talked about in class. It is specific for reducing esters to aldehydes and no further. Doesn't reduce them any further than that. And so the product of this, the major organic product at least, by which we mean the largest organic compound, will simply be the corresponding aldehyde, which looks like this. And you will also get a molecule of methanol. That's where the methoxy group goes. But as we've mentioned in class, first of all, nearly all esters, probably 99.9% of esters that you're going to run across are going to be methyl or ethyl esters. And in reactions like this, you will get methanol or ethanol, respectively. As a side product, both methanol and ethanol are soluble in water in all proportions. So they will wind up in the aqueous layer when one does the aqueous organic extraction. And so they will wind up being taken out of the organic part of the mixture and will wind up in the waste jug. So the major organic product that will get isolated would be this aldehyde. And let me show you another thing while we're at it. This is not something I've stressed much in class, but just for those who are interested and curious about such things, There is a standard abbreviation for the aldehyde group that you may use if you like. And that abbreviation is CHO. And in recent years, I've taken to avoiding using these abbreviations because I understand that often they can be confusing. Certainly, when I gave this problem on the exam, I expect nearly all of the people who got it right drew the structure like this. But just so you're aware, CHO is a perfectly acceptable abbreviation for an aldehyde group. And you may use it whenever you're drawing a structure without needing to be concerned about exact locations of electrons. In other words, if you're doing a mechanism, this kind of structure that we just drew up here would not work. If you're drawing a mechanism, then you would want to draw the entire structure out and most likely put on the lone pairs onto the carbonyl oxygen. But if you're just drawing a structure and that's it, this other version of writing that structure is perfectly acceptable. You can feel free to use it. If you don't like it, you don't have to. It's totally optional. So in the next question, we're treating this ketone with a primary amine and the conjugate acid of that primary amine. In other words, we're under acidic conditions. And again, the way you know you're under acidic conditions is if you're given a cation that is not an alkali metal ion or other metal cation. And that's certainly the case here. This is an organic cation. And this is a major reaction in chapter 19, where we learn that if you treat an aldehyde or a ketone with a primary amine under acidic conditions, you will get the imine. In other words, you'll go from C double bond O to C double bond N, and the nitrogen that's in the primary amine will wind up being double bonded to the oxygen. And you will also make, in this process, a molecule of water, which of course, to an organic chemist, is simply an inorganic side product. So we need to attach this isobutyl group here. Let me make sure to do this right. So there's the alkyl chain. Whoops, and then we want to put a nitrogen here. So we go from C double bond O to C double bond N. So you get the corresponding imine. Just let me double check that we have the right number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the product should have 11 carbons also. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's the structure of the product. And of course, that there's no stereochemistry to that double bond. There's no cis-trans distinction. So you would get the corresponding imine. Imines are also called Schiff bases. So this is an imine or Schiff base. Biochemists call imines Schiff bases, and imines are super important in biochemistry. There are some processes that depend on imine formation, and so it's a really key intermediate structure in some of the biochemical processes. The next reaction involves treating the same ketone with sodium cyanide in water. And we learned that this is the necessary conditions for making a cyanohydrin. And let's not forget what the cyanide ion looks like. Don't forget that it's C triple bond N. Both the carbon and the nitrogen have lone pairs on them, and the carbon has a minus charge. So that's the structure of the cyanide ion. Please be sure you learn it. You will need to know that structure if you need to use it in any mechanisms. The cyanide ion shows up a lot in a number of different organic reactions. So the question first, before we begin to write the structure of the product, even though it's actually not going to affect the structure of the product, it's worthwhile to consider this. Are we under alkaline conditions or acidic conditions? We already said that acidic conditions involve being given a cation that is not a metal cation, that's some kind of organic cation. And alkaline conditions involve an anion that is not the conjugate base of an extremely strong acid. In other words, anions that are conjugate bases of extremely strong acids are things like Cl minus, Br minus, HSO4 minus. Those are the conjugate bases of very strong acids. And those are not the anions we're talking about in alkaline conditions. In alkaline conditions, you will find anions like OH minus. OH minus is the conjugate base of water. Water is not an extremely strong acid. Or CH3O minus. CH3O minus is the conjugate base of methanol. Methanol is not an extremely strong acid. And the cyanide ion is the conjugate base of HCN, which is, again, not an extremely strong acid. So having the presence of an anion that is not the conjugate base of an extremely strong acid means that we're under alkaline conditions. This also implies understanding that NaCN means this. It means the cyanide ion. And if we were to draw the mechanism, we would not use the sodium ion at all in the mechanism. So in any case, we're going to form the corresponding cyanohydrin. And hopefully you remember this from class. This means that the carbon which had been involved in the carbonyl is going to be attached to an OH group. So we've essentially gone from C double bond O to C single bond OH. And the other bond goes to a nitrile group, a cyano group. And if you want to, you can draw out the triple bond. You don't have to unless the question specifically says to. So if you want to draw C triple bond N, that's fine. Or again, you can abbreviate it, just like this. Either way is perfectly acceptable. Since we're only drawing the structure, we're not doing mechanisms, and so using these abbreviations is certainly acceptable when you're just drawing the structure. So this is a cyanohydrin. Cyanohydrin. Good. And so those were the only questions that I had on this past exam that were directly related to Chapter 19 and were of the type where you fill in the structure of the product. So moving on in our worksheet, and as always, I've given you some hints on where to start. We had a couple of mechanisms. The first mechanism involves treating this ketone with excess benzyl alcohol, and we also see the conjugate acid of benzyl alcohol. So once again, we're working under acidic conditions. I would say most of the reactions in Chapter 19 occur under acidic conditions. And the key feature of all reactions under acidic conditions, without exception, is there's going to be a cation there that is not a metal cation. In this case, the plus charge is on an oxygen. It's the conjugate acid of benzyl alcohol. And we get the corresponding acetal. So we've added 2 molecules of benzyl alcohol and lost a molecule of water, and we get an acetal as a result. So that's one of the reactions in Chapter 19. The second question involves taking a ketone and treating it with now a secondary amine. Before we had a primary amine, this time we have a secondary amine and its conjugate acid. So once again, we're under acidic conditions. One of the species we're given is a cation that is not a metal cation. So we know in both of these, we'd better draw our mechanisms in such a way as to make sense in acidic conditions. The product at the end is an enamine, and that's what you will get by treating a ketone or aldehyde with a secondary amine in the presence of an acid catalyst. Once again, we will lose a molecule of water. So since it takes so long to draw mechanisms in ChemDraw, I figured it would be easier just to use the answer key, which has the mechanism already. And we'll have gone over this mechanism in detail in class, but let's go over it again. So we're back to this first question. where we go from this ketone to the corresponding dibenzyl acetal upon treatment of the ketone with excess benzyl alcohol. Benzyl alcohol is effectively the solvent in the presence of an acid catalyst, which will generate some of the conjugate acid of the benzyl alcohol. So we're in acidic conditions. And as we've said in class, hopefully made pretty clear, when you're under acidic conditions, most likely the first step is going to be protonating that carbonyl oxygen. And the reason that we do that is because if we just immediately attacked the carbonyl carbon and broke the carbon-oxygen double bond, that will generate a minus charge on the oxygen, and that's no good, not in acidic medium. In alkaline medium, we can do that. In alkaline medium, you can rationalize having such strongly alkaline species in solution, not in acidic medium. So in acidic medium, we need to protonate that carbonyl oxygen first before we do the nucleophilic attack. And the species that you need to use to put that proton on the oxygen is always going to be the acid that you're given. Whatever is listed above or below the arrow, that is the most acidic species. And most likely it will have a plus charge. So that's what we're using here. This is the conjugate acid of benzyl alcohol. We have an arrow starting at one of the lone pairs on oxygen, and ending at one of those hydrogens on the conjugate acid of benzyl alcohol. So we form a new oxygen-hydrogen bond. We break this oxygen-hydrogen bond and push the electrons onto the positively charged oxygen. So we lose effectively a neutral benzyl alcohol molecule. By the way, you'll notice that I also just added lone pairs to the structure I was given rather than redrawing it. You may do the same thing if you run into a first step like that. That's totally fine. Save you some time in drawing that structure out. So here we have our protonated species. And what we've done in protonating that oxygen is we've made this already partially positively charged carbonyl carbon even more electrophilic, because now the species has a full plus charge on it. So now we're ready for nucleophilic attack. And the way you know what to use as your nucleophile is, again, by looking at what you're given. And you want to pick among the species that you see the most nucleophilic one. And that in this case is benzyl alcohol. You'll notice that I'm not using the benzyl oxide anion, PHCH2O-. There is no such thing. Alcohols are not strong acids. So you will not see any concentration, at least at any reasonable concentration, of the conjugate base of the alcohol. That's not going to happen with alcohols. They are not nearly acidic enough. Most alcohols of a pKa, give or take, round about 18. So if we're here in perhaps a solution with a pH of 1, we're much too far away in terms of pKa difference for us to be able to rationalize using a benzyl oxide ion. So benzyl alcohol itself attacks that carbonyl carbon. Do not be afraid to do so because the H is there. We'll take care of the H later. So use the benzyl alcohol molecule. In this case, it's benzyl alcohol. It's going to be some kind of alcohol, but just use whatever alcohol you're given. That's going to attack the carbonyl carbon and break the carbon-oxygen pi bond, pushing the electrons onto this oxygen and getting rid of the plus charge. So that gives us an intermediate that looks like this. And those are generally going to be your first two steps in acidic solution. Protonate the carbonyl oxygen, nucleophilic attack on the carbonyl carbon with whatever you're given, that's a nucleophile. And so that gives us this intermediate. It's at this point in the mechanism that we typically have to do some proton transfers. The goal in doing the proton transfers is always going to be losing a molecule of water. At least in chapter 19, that's a pretty common strategy, is losing a molecule of water. So we need to pull off a proton from this oxygen first. The idea is we want to get rid of the plus charge before we go protonating elsewhere. Some people want to put the proton onto the other oxygen first. And it is correct, we are going to put another proton onto that oxygen. But if we did that first, we'd wind up with an intermediate that has a +2 charge. And I think you'll agree that doesn't make a whole lot of sense. Much more sensible to go from a charge of +1 back to 0 and then protonate that other oxygen. So that's exactly what we'll do. We need to pull off the proton on this oxygen in order to make that oxygen go from a charge of +1 to 0. And now all we need is a base that can do that for us. And the way to find the base is, again, look at what you're given and pick whichever species has the most electron density on it. In this case, benzyl alcohol, which acted as our nucleophile a moment ago, is also the strongest base that we have in solution. We don't have any stronger bases. That's the strongest base we have. We're in acidic solution. There are no very strong bases. It wouldn't make sense to have a strong base in acidic solution. So use, again, whatever alcohol you're given to pull off this proton. The electron flow starts at the oxygen atom on the alcohol and ends at the hydrogen that's attached to the oxygen with a plus charge, whereupon we also break this hydrogen-oxygen bond, push the electrons onto the oxygen with the plus charge, and wind up with an intermediate that is a total charge of 0. And this is your hemiacetal intermediate. And you're going to get a hemiacetal intermediate in any reaction that involves forming a full acetal. And now basically we'll lose a molecule of water and then repeat those steps again to wind up with the full acetal. In order to lose a molecule of water, we first need to protonate the OH group. We can't lose hydroxide ion in acidic medium. That's not going to work. OH minus is much too strongly alkaline to exist in acidic medium at any reasonable concentration, at any concentration that we can rationalize its formation. So we need to protonate that oxygen first. That will make it easier to break this carbon-oxygen bond and lose the water molecule. So we need to protonate the oxygen. That means we need an acid. We'll use the exact same acid that we did before. Go back and look at what you're given and pick whatever is the most acidic species. In this case, it's the conjugate acid of the solvent. That's generally what it's going to be. So again, the electron flow starts at the OH group, ends at one of the protons on the acid. Then we break the oxygen-hydrogen bond. Of course, there's multiple correct ways to show that. If this arrow had gone over instead of under, it would be perfectly acceptable. So there's always multiple correct ways to draw a mechanism. But we break that OH bond, we push the electrons onto oxygen, and we've protonated that OH group. That gives us this intermediate, and now we're ready to lose water as a leaving group. And in order to help us lose that water molecule, the oxygen on this benzyloxy group can help out by pushing in an electron pair, forming a pi bond to that carbon, and breaking the bond between that carbon and the water molecule. That gets us to this intermediate, which I want you to notice looks very, very similar to this intermediate. The only difference is in one case we've got an H, in the other we've got a benzyl group. But it's a very similar intermediate. And just like we had a molecule of the alcohol attacked before, we're going to have the same thing happen again. An alcohol molecule will attack the carbonyl carbon, which was already electron poor, made all the more electron poor by virtue of the particle having a full plus charge on it. So the alcohol attacks, we break that carbon-oxygen pi bond and push the electrons onto the positively charged oxygen. That gets us this intermediate. And then all we need to do to finish the mechanism is deprotonate this oxygen to get rid of the plus charge. We will once again use a benzyl alcohol molecule or whatever alcohol you're given. The electron flow starts at the oxygen of the alcohol, ends at the hydrogen on the positively charged oxygen. We break that hydrogen-oxygen bond that pushes the electrons onto the oxygen, gets rid of the plus charge, and we have our neutral acetal. So that's a very typical acetal formation reaction. Be sure you're familiar both with this type of acetal formation and with the type where we get a cyclic acetal. It's possible to make a 5 or 6 membered cyclic acetal. And there's notes on that in the class notes, but it's the exact same mechanism. They're not different reactions. They're exactly the same thing. Good, so much for that reaction. That leaves this next one in which we're forming an enamine. We're taking a ketone, treating it with a secondary amine in the presence of an acid catalyst that will generate some of the conjugate acid of that secondary amine, and we'll wind up making an enamine. And that's a typical enamine formation reaction. It'll involve a ketone or aldehyde, and as long as that ketone or aldehyde has at least one alpha hydrogen attached to it, then you will be able to form this carbon-carbon double bond and make the enamine. In fact, let me just pick up this whole thing and transport that into ChemDraw in case I need to make any comments. So this over here is an enamine. There we go. And so when we look at what we're given, once again, I see a cation that's not a metal cation. That tells me we're under acidic conditions. And so we will proceed as such. And again, in acidic conditions, maybe not 100% of the time, but most of the time, the first step is going to be protonation of the carbonyl oxygen. And so we will use whatever acid we're given in order to perform that protonation. So again, I've added lone pairs to that oxygen, and we'll use this acid, that's the acidic species that we're given. We'll show protonation starting at the lone pair on the oxygen, ending at one of the hydrogens on the acid, and then breaking the NH bond that will get rid of the plus charge on nitrogen and give us this intermediate. Just like before, we've got a protonated carbonyl species, and that's now an even more powerful electrophile. But again, in acidic medium, we need to protonate that carbonyl oxygen first. Certainly, we will need to do that if there's going to be nucleophilic addition to that carbonyl carbon. Otherwise, we'll make O-, and that's again invalid in acidic medium. If we were in alkaline medium, we could do that, but not in acidic medium. In acidic medium, if we're going to get nucleophilic addition to a carbonyl carbon, we need to protonate that carbonyl oxygen first, so as to avoid getting that negatively charged intermediate. Once we've formed this intermediate with the protonated oxygen, then our nucleophile can attack. And when I look back at the two choices of species I'm given, I think you'll agree the free amine, not the acid. The free amine is by far more nucleophilic. The acid can't act as a nucleophile. So the electron flow again starts on the lone pair on the nitrogen of the secondary amine, goes towards the carbonyl carbon, the electron poor carbonyl carbon. We break that carbon-oxygen pi bond and push the electrons onto the oxygen atom, thus getting rid of the plus charge. That gives us this intermediate over here. And lo and behold, once again, we're at a situation like before. The steps were just the same in forming the acetal. Protonate the carbonyl oxygen, nucleophilic attack on the carbonyl carbon, and then what did we do? Proton transfers. The idea is we need to get a proton off of this nitrogen and put a proton onto the oxygen. By the way, a common question, and one I expect to address in class, is why can't we save ourselves some trouble by just having this oxygen pull off that proton? And it's a very fair question, and the reason that doesn't happen is because you would get a 4-membered transition state. And the way you know that is by counting atoms. 1, 2, 3, 4. If we count atoms between the oxygen and that nitrogen, you will see that we count to 4. That oxygen's 1, this carbon is 2, the nitrogen atom is 3, and the hydrogen atom is 4. So between the oxygen and the hydrogen on the nitrogen, you have a four-membered transition state. It's like they're forming a square. And as you are no doubt aware about four-membered rings, they are very strained, and they do not form terribly easily. And essentially, the oxygen can't reach around far enough to get that proton on the nitrogen because it's a four-membered transition state. Interestingly, if it were a 5 or 6-member transition state, moving that proton in one step would be very easy. And that happens all the time in biological systems. But with a 4-member transition state, no way. We can't do that. So that's why we need to take care of this in 2 steps, not just 1. Again, it makes sense for the first step to be removing the plus charge on this intermediate. We're not going to protonate the oxygen here and make an intermediate with a +2 charge. That wouldn't be very sensible. So we'll first remove the proton on whatever atom has the plus charge and then protonate the OH oxygen. So the only question that remains in the decisions that we make is what are we going to use to pull that proton off? Not a water molecule. There is no water. You're not given water as an option. So you'll use whatever among the species that you're given is the most alkaline, and that's going to be the amine-free base, certainly not the conjugate acid of the amine. So we'll use that molecule to pull the proton off. The electron flow starts at the nitrogen, the electron-rich nitrogen atom on the amine. We draw an arrow to the proton that's getting removed. We break the NH bond, and we push the electrons onto the positively charged nitrogen. That gives us this neutral intermediate, which is very similar to what happened before with the acetal. Now we can go ahead and protonate this OH oxygen, and we will use the acid that we're given in order to put that proton on. The acid that we're given is the conjugate acid of the secondary amine. So the electron flow again starts at the OH oxygen. We draw an arrow to the proton that's on our acid. We break the nitrogen-hydrogen bond. In so doing, we have to do that. Otherwise, the hydrogen will have 2 bonds, and that's no good. So we break the NH bond. We push the electrons onto the nitrogen to get rid of the plus charge, and that gives us this intermediate. And now we're in a really similar situation to what we found with the acetal. We're now ready to lose a water molecule. And so the nitrogen in this carbon-nitrogen bond can help out to expel the water molecule by donating its electron pair inward and forming a carbon-nitrogen pi bond. So we form a carbon-nitrogen double bond, we lose the water molecule, and we get this intermediate. And it was at this point, if this were forming an imine instead of an enamine, we would now simply deprotonate the nitrogen to get rid of the plus charge. We don't have that option. There's no hydrogens attached directly to that nitrogen. So we need to get a proton from elsewhere. And the place that we get it from is the beta carbon. Let me get myself an alpha and a beta over here. Symbol. So remember, the alpha carbon is going to be the one that's next to the nitrogen, and the beta carbon is going to be the next one out. So when you're forming an enamine and you're looking for a place to pull a proton off, it is always going to be the carbon that's beta to the nitrogen. Always. There are no exceptions. And by the way, there are 4 such protons. There's 2 that are attached to this beta carbon, and there's also 2 more on the other side that are exactly the same. So it doesn't matter which proton you pull off. And in pulling off that proton, we'll be able to move the electrons toward the nitrogen and get rid of the plus charge on nitrogen. That just leaves one decision to make, which is what are we going to use as our base to pull that proton off? And the answer is just like before. You use whatever among the species that you're given is the strongest base, which is once again going to be that secondary amine. That's going to pull the proton off. A very common question is, how come I can't use a water molecule? to pull that off. After all, we just made a water molecule over here. And that is once again a very fair question. The reason that we cannot use a water molecule is because we're only forming one mole equivalent of water. We just get one water molecule for every ketone molecule that goes through this reaction. But we have thousands and thousands of mole equivalents, maybe more, of that amine. That amine is effectively our solvent. And so since the amine so drastically outnumbers the water molecules, it makes much more sense to use the amine as the base. So in general, that's what you'll do. When you're looking for a base in acidic solution, you'll take whatever the most alkaline species is of the species that you're given. Sometimes that might be water. We'll look at reactions that occur in aqueous acid later on, especially in chapter 21. But here, these conditions are anhydrous. There's no water present. The way you know there's no water present is because H2O is not mentioned above or below the arrow. So the amount of water that's present even after this molecule of water is produced is minuscule. It's much too small to affect the outcome of the reaction. So it makes sense instead to use the amine as our base. So that's what we'll do. We'll draw an amine molecule. We have electron flow. We have electron motion from the nitrogen that's in the amine. We start the arrow there and we end it once again at the hydrogen, at the proton that we're going to pull off. So that forms a new nitrogen-hydrogen bond. We then use the electrons in the carbon-hydrogen bond to move inward between the carbons that are alpha and beta to the nitrogen. In other words, the electrons in the CH bond remain attached to the beta carbon and swing inward to form a carbon-carbon pi bond between the alpha and beta carbons. And then we're not done. We need to break the carbon-nitrogen pi bond. If we didn't, then the carbon I've labeled alpha would have 5 bonds. So we need to break that carbon-nitrogen pi bond. We push the electrons onto the nitrogen atom. That gets rid of our plus charge, and we get our neutral enamine as the product. So that's pretty much it for the chapter 19 worksheet. I hope that was helpful, and we will keep doing these. I think the next chapter after 19, incredibly enough, is 20. So thank you all for joining me. We will end it there for now, and I will see you all later.